ALD journey started long back in around 1974 when the scientist Tomo, when he at that time he was working with the PhD and working on the electroluminescence devices, and in these electroluminescence devices how can you stabilize for that time, because the display around that time is becoming more prominent. How can you large area display as well as stable display you can produce. So that time it was atomic layer epitaxy. So that time also you send some chemical gases and then you can do the deposition. I will later explain one by one what is this process, and then mostly it started with the thin film devices and display devices, and then around 1987 and now around 1990, so it's come into the more picture in the silicon industry. You know, the silicon, the size of the devices is decreasing, and you are having the gate scaling also, and you are having not the planar MOSFET, you are having FinFET and gate all around transistor. So on those devices, how you can uniformly coat, like if you have a FinFET, like this is a strip fin, so in the top and both the side wall deposition you have to do together conformally. So that is the one other application in the atomic layer deposition. And also you want to, when the replace the silicon dioxide for the gate scaling, because you want to decrease the VDD, so you have to decrease the threshold voltage, so you want to decrease the gate oxide thickness. But if you decrease the gate oxide thickness too much, the leakage current will increase. So the possible way is to use the high K dielectric. So either hafnium oxide or other high K dielectric. So those are the major things. And how can you deposit very thin layer of hafnium oxide, very high quality in terms of electronic grade. So you have a less interface trap charge or fixed charge in this gate oxide. So that's why this ALD become more prominent in the silicon industry. Now apart from this silicon industry, there is another application. Professor Vamsi already explained this different deposition technique, either chemical deposition or physical method, physical vapor deposition. But if you want to do the above, all those deposition technique, they have some advantage and some disadvantage. So you start from the simple thermal evaporation, e-beam evaporation, sputtering. But when you want to deposit more conformally and thickness control way, then you have to do the CVD or ALD or even e-beam also can do some extent. Because in the device fabrication, you want to do the large area like 12-inch wafer nowadays is processing in the TSMC or Samsung fab. So where you want to like 12-inch wafer, so you have to do uniform deposition, conformal deposition and thickness control in nanometer scale. So it is nanometer mean I want to deposit only one layer of Al2O3 and second layer of Al2O3, or I want to deposit 1 nanometer of chrome or 2 nanometer of gold, like that. That precision you need wherever I want to stop. And they have a lot of application. As I mentioned, this is the FinFET one, and you can see this is the FinFET, like the gate is like this is the top and both the side gate are working, and you have the thin layer of SiO2 because you use the sometime of the very thin layer. Thin layer means 1 or 2 layer of SiO2 thickness. So it will be less than around 0.5 nanometer or something like the SiO2, and then you use the high K dielectric, mostly hafnium oxide is used, and this is around 1.9 nanometer. And you know the hafnium oxide is around 24 dielectric constant, so you can get 6 times electric field, like if you use the same thickness of hafnium oxide and SiO2. So you can increase the field, and then you have the metal, gate metal. That also you want to uniformly deposition by all this top and this side wall. But if you do the deposition by sputtering, so this layer will be deposited on the top will be high thickness, but in the side wall no thickness or very less deposition. Either you do the e-beam or if you do the sputtering, all those deposition. But using ALD, atomic layer deposition, you can uniformly, here you can see this direction and this direction the same thickness, and this is precise control. That's why this is important. And also nowadays lot of application in the energy application, like you want to make the different types of metal catalyst for the energy conversion or very thin layer of metal, and even for the like this other emerging area like the aerospace engineering, like you want to do uniform coating for some ununiform surface, like you want to make a big antenna, like antenna means this big structure antenna, and you want to do like a few metal layer of coating to absorb like particular radiation from the space. So that time you need very uniform control, and that you can uniformly coat by atomic layer deposition. Also this biomedical application, and also this semiconductor display technology, which had started very long back, because you want to make the display curved display or any shape display. So there you have to do the uniform deposition. So those are the area along with this detector are applicable in the ALD, and these are the other more, if you want to do more complex structure in the semiconductor industry, like if you have a very high aspect ratio structure, also FinFET, or any other application you are making, like this is very high aspect ratio. You can see here the aspect ratio is very high, like this is like 5 times larger than the high, like this lateral direction and this depth. So if you want to deposit uniformly, like you can see like side wall as well as top, they are uniform deposition of the metal or insulator, you can deposit it using atomic layer deposition. Not only the 3-5 industry, like in the not only semiconductor industry, but 3-5 industry also started using the ALD, because this high K dielectric for the 3-5 HEMT or these devices, like where you want to use the either you want to use the Schottky gate or source drain contact, that also can be possible along with the normal MOSFET, like 3-5 MOSFET also. So these are the all application, like the from display to emerging electronics, photovoltaic, catalyst, or like our aerospace application, all this application is mentioned here. So what does ALD do? It is the full name is the atomic layer deposition, and it is mainly the gas phase thin film deposition technique. And these deposition techniques you can control layer by layer growth, like one atomic layer, another atomic layer. So that is the major advantage. And conformal deposition, I will come to how to main, but so this again I will discuss, I will not spend this term. So conformal deposition means like you have a structure, like I want to do the liquid phase process, like you done the Searles process, now you dip it. So the deposition like here will be uniform, but here where you have a small pore, there will be, it will fill up because of the surface tension. So you don't have control. These are very small structure, like if it is in the 500 nanometer or something. Like, but if you have a gas phase like the PVD, like sputtering or all these things, then what will happen? Sputtering or e-beam evaporation. If you do deposition, here the thickness will be very thick, and side wall, or here you cannot deposit, even you cannot deposit this side. And if you do the even CVD process, there also you can give most of the deposition will take place here, but side wall and this here inside it will be little bit deposition. But compared to this is at least you will get some deposition here. But if you do the atomic layer deposition, you can uniformly do these things. So that is the major advantage for the atomic layer deposition. You can do conformal deposition as well as single atomic layer by layer control deposition, thickness control. And another is it is a pinhole free. Like if you do the sputtering or sometimes even other deposition, in the film you will see, if you see in the ACM or things, or even in the sometimes optical microscope, if the pinhole is bigger, so it is not uniform. So there is a pinhole. For the electronic grade material, like the if you want to make device, so the if I use deposition dielectric, so there is a pinhole, the leakage current will happen. So you need to have a pinhole free single layer or 2 layer or 3 layer. So that is the major advantage. You can do that using ALD. And current worldwide ALD can be used many deposition, like you can do lots of oxide. So here you need 2 types of precursor. One is the ligand precursor to prepare the surface for the next layer and define the kind of material growth. Generally for the oxide, we have to make you have to pass the water vapor, and then hydrogen bond OH group will bond to the silicon substrate, and that will act as a ligand precursor. And then the main precursor that is the metallic or different what type of material you want to deposit, that will determine this precursor, and this precursor will bind to that surface, and then you heat up, so the byproduct will be removed. So the major, like what are the condition for this precursor must be volatile. Otherwise, if it is bind strongly to a substrate, after reaction takes place in locally, it cannot be removed quickly. So that, and this precursor has to be chemically absorbed by the surface of the substrate. So if you take, so that's why proper substrate also needed, like not all the substrate it can be deposited, where the chemically absorbed, like there is like chemical kinematics, like what is the transfer of the either what is the energy of the surface and the chemical. So, they are do the local reaction on the surface, and you can prepare the preferred surface site on the substrate also, that will enhance the growth also. So, those are the, and also the major thing is that should be self decomposed, that means it will do the reaction and byproduct will be coming out, and so that will be self decomposed. And maybe you have to give some temperature also, sometimes some of the ALD things, like it can vary mainly 50 to 100 degrees Celsius to 500 degrees Celsius, or you can do the plasma enhanced ALD also, low temperature process. So, suppose I am giving the example for the Al2O3 oxide deposition. So, first what you do, you take a silicon substrate, and then if you pass the water vapor, then hydroxyl bond will take place in this surface, and uniformly throughout the silicon substrate this hydroxyl. And then once this cycle is done, then I stop the water vapor flow, and then I send the nitrogen carrier gas. So, there is no water vapor in the chamber. Now, then the second step, I started the flowing of the main element, that is suppose for the, in this case TMA, trimethyl aluminum. So, now once you send this gas, so this gas, this molecule will now try to bond here. So, depending upon the temperature, this growth rate, like how long you have to send this gas. So, if you increase the temperature, the bond rate will increase, but you cannot give to very high temperature, then because this although bond will take place and again high temperature, then it can coming out from the, break the bond and it can go out, decompose also it takes place. So, you have to find the proper window of the temperature, like which will do this process. So, then once is taking the bond, and then you can do pass more gases of this TMA, and then all the hydroxyl will make the bond with the TMA. Now, you stop flowing these TMA gases, and it already pumps is there, which is taking out the excess these TMA gases. Now, there is no TMA gases, then one cycle is finished, and then again second cycle you pass again water vapor, then again it will make the bond on that surface, and then this cycle will continue. So, by controlling the cycle and proper given times, so you can control layer by layer growth of Al2O3. So, that is the, and you can see here it is chemically absorbed by the substrate. So, your substrate is here, so the gas will come go inside and chemically absorb. So, it is not directional growth. So, it is more conformal growth is taking place in this ALD system, and you you can do the like the layer by layer growth, and it can be done. You can watch the some videos, like I am not playing because of the time. So, you can watch in, there is a lot of YouTube video if you really understand how this chemically absorb, like we have the system from the Benek, they also have a video in the YouTube, you can search it and watch it. And the in the ALD system, so the growth rate is determined by the growth per cycle, because I am sending the cycle by cycle the precursor. So, the growth rate is changed by growth per cycle. So, this is the cycle and thickness, and if you find out the slope, that you can find out what is the growth rate, and this growth rate is depends upon different parameter, as I say, because it is chemically absorbed. So, chemical kinetics is the important, or chemisorption, and that depends upon the what is the reactivity of that ligand with the or that precursor with the surface, and number of sites available on the surface. Like number of sites, like if you take the silicon 111 surface and silicon 100, density of the like the silicon on the surface atom, their arrangement also different, dangling. So, the number of dangling bonds will form on the silicon 111 surface and silicon 100 surface will be different per unit area. So, that is why like the number of sites also is important, and also it is depends upon the substrate types, what type of substrate you are using, and obviously the temperature. And as I meant, the temperature is a major factor. Like if you do very low temperature, then what will happen? The material is coming and they are just sitting, physically sitting. They are not chemically react with your substrate. So, the chemical bonding will not form. So, that is like the physioabsorption take place. But if you do give the little bit temperature, then it will chemically absorb, like they make the proper bond and they will sit. So, that the temperature window, but if you give very high temperature, what will happen? This material is coming and then it taking evaporation is taking place. so it will not see. So this window is important, and different precursor has, you have a specified window, so you have to do the deposition or the growth or that temperature of this. And we have the system like the for ALD system, we have a Benek ALD system, and you know the ALD as I mentioned at the beginning, who is the inventor, is from the Finland. So the major company like the two company, all the Cambridge Nanotech is there from the UK, but the major company like the Benek is another Finnish company also there. So the both of them are from the Finland because of the history, because the most of the ALD activity started at the beginning in the Finland. So this is the we put the wafer, but you can deposit very large area because it is a chemical absorption. So you can put 6-inch, 12-inch wafer and you pass the gas, so all substrate area. So there is large area deposition. You don't have any problem. You can put this house and then you put a big antenna. Nowadays people are doing you know the space telescope, they are very big, but you want to do for conformal deposition, very thin layer. Like I want to absorb some far infrared, you know the H1 radiation, H2 radiation, those radiation if you want to absorb, so they reflected properly. So you have to do the multi-layer coating on those material, very thin layer. So that can be done using the atomic layer deposition. And you have the process control, because you have to control the precursor flow rate as well as the temperature and the carrier gas as well as the purging gas. So those things those are electronics control. So if you program it, how much cycle, this cycle, so we can program, and how long you want to deposit. So it can be done in this system. And if you see closely, so currently we have only the Al2O3. Now we are trying to purchase the hafnium oxide precursor also. So we'll be able to do hafnium oxide as well as Al2O3 deposition. So these are the requirement. So this is the typical cycle. So we can do 100 degrees Celsius to 350 degrees Celsius, and this is the pressure, and you can do the 1 by cycle, like the pulse ligand precursor, that's mean water vapor, and then the TMA flow, and then again you have to give the purging gas. Why is it important? Because you have you have to remove all the TMA gases. Otherwise what happens, if you start that, then layer by layer growth, you don't have the control by layer growth. So this cycle is important, like the purging and then ligand precursor and main precursor. And so this is all, and this I already discussed. I'm not going more details again one by one, but you can go through those. So if you have any question, and so what are the application you can do? So like if you want to make the 2D materials field effect transistor, suppose if you want to do, so you transfer the flake, simple, and then you want to top gate if you want to make. So then first you have to deposit, suppose I have a substrate here. So you want to make a top gate devices. So you take a silicon SiO2 substrate. So this is 300 nanometer SiO2. You transfer a flake here. Okay. So you all of you can do transfer or by chemical or CVD method. Then what will happen? You do the ALD deposition. So the oxide is deposited, Al2O3 is deposited, and then you do the lithography, which has explained recently. So you open by lithography these two contact windows, source and drain contact. So you do lithography, and then you open this. Everywhere the photoresist is coated, and then you do the BHF dipping to remove the Al2O3 from this area. So I remove the Al2O3 from this area, clear? And then after that I have to make the source drain contact and gate contact. So now in the then you remove the photoresist, and then again second level lithography, you do the lithography and do the this is the source contact and this is the drain contact, and same metal you can put or different metal you can put for the gate. So that way you can make the top gated field effect transistor. This is simple example, but you can make the complex devices using this e-beam evaporation, lithography and ALD techniques.